All right, so recursion is when a method calls itself. And this might seem like a bad idea, but there are many interesting problems where recursion ends up being simpler than a regular loop. And I'll show you some examples. Those problems we did in the warm-up, both are easily done with recursion. I'm not going to say it's easier, but either of those can be done with recursion, and we will do them. But all that said, any problem you can do with recursion, you could do with a regular loop, and vice versa. So we know a method is recursive if it has two properties. One is that it has one or more calls to itself. If it doesn't have a call to itself, it's not recursive. And then it also will have what we call a base case, and that's an if statement, a conditional statement that gets you out of the looping. Otherwise, the looping goes forever, right? And that would be an infinite loop, which would not be good. So here is an example. This calculates the factorial of a number, which we just did in the warm-up I used a for loop. So let's walk through this. So here's this method, factorial, int n. You send in an integer n. This is the call to itself. This is the recursive call where it says return n times, and then it calls itself with the number one smaller than it was. So let's say you send in 5. Then it's going to come down here and say, well, we're going to send back 5 times, and then whatever you get when you call it with 4. And the 4 one will, it cascades, it builds on itself. This top if statement is what we call the base case. That's where, notice it doesn't call itself inside of that if. This is like your way out. Any recursive function has to have a way out, otherwise, it would go forever. So this says, hey, if n is 0, if you finally call factorial 0, it's just going to return the number 1, and then all the recursiveness will wrap itself up. So, so here's that same function, and I'm just going to walk you through what happens. So if you call factorial 4, in case it's not, I should say, I mean, we just did it on the warm-up, but in case you're not familiar with it, factorial of a number is that number times all the integers under it down to 1. So 4 factorial is 4 times 3 times 2 times 1. But if you call 4 factorial, over here on the right, I say 4 is not equal to 0. So it returns 4 times factorial 3. Okay, and when we call factorial 3, 3 is not equal to 0. So I say called here, it really should say returned. And the 3 calls the 2 calls the 1, and the 1 is going to call 1 times factorial 0. Now, finally, 0 is 0. That's this line up here, if n equals 0. So instead of calling it recursively, it returns a 1. So then it actually, you can imagine, it just goes right back up the chain. So this bottom one puts a 1 right here. You have 1 times 1. And then that answer goes up to the line above. So now we have 2 times 1. So we're going to get a 2 right up here. I think I wrapped it up too fast. But anyway, 2 times 3 is 6. And then the 6 goes up. And then finally 4 times 6 is 24. So basically, it sets up a bunch of things, and then it wraps it all up on the way out. Questions? Don't worry, we'll practice. Here's another example. So this one, you send in an integer, and it prints that number and a space. And if the number is greater than 0, it calls the function, it calls itself again with a number 2 less. Okay, so if we run it with 5, let's see what happens. 5 is printed, and the base case is checked. This is the base case. 5 is greater than 0, so it calls it with 3. It prints a 3. Right over here is where the output is. It checks the base case. 3 is greater than 0, so it calls it with 1. Great. Calls it with 1. 1's printed. Base case is checked. By this, I mean 1 is greater than 0, so it calls itself again. Calls it with -1, and I had to make those 2 lines smaller. Sorry if that's confusing, but it calls it with -1, prints the -1, and the base case is checked. And since -1 is not, this is a mistake. It's not greater than 0. The method execution ends. So just boom. This was just printing things. Here's another one. You may have heard of Fibonacci numbers. They're an interesting sequence mathematically where it starts. The first 2 numbers are usually a 1 and a 1. Sometimes it's a 0 and a 1, but a 1 and a 1. And then to find every other number, you just add the previous 2 numbers. So this method gives you the nth Fibonacci number by recursively calling itself, adding 2 previous numbers until we get back to the first 2 ones. So what I mean is if I sent the number 6 into this, we would get the 6th Fibonacci number, which would be this number 8 right here, because the first number is a 1, the second number is a 1, third number is a 2, and so on. I don't think I walk us through that one. But let's look at it visually. This is kind of a double base case. It's like, hey, if sorry, I'm just bothered by it not being consistent. If n is 1 or 2, then return 1. That's these 2 1s at the beginning. And then otherwise, return the previous number plus the number before that. So it's like magic the way these things work. Honestly, it's just crazy. So let's take a look. I've got 2 more examples and then we'll start practicing. This one, I tell you, it's going to count down from n to 0. So if you called countdown 5, it would print 5, 4, 3, 2, 1, 0, 1 number on each line. And that's because it comes in, it prints the number, and then it checks, hey, if the number is still greater than 0, then call it with the number 1 smaller. And cool. But check this out. I switched it. So this one's slightly different. The print is after the base case and after the recursive call. So if your print line is after the recursive call, the output's gonna come backwards. What happens is none of the printing happens at all until the recursion ends, and then it goes backwards. So we're gonna trace it. But bottom line, let's look at these 2 versions. So we've got this one where we have, it's basically, I think it's the same code, except I just moved the print line after. So here's, if the print line is before, you're gonna get 5, 4, 3, 2, 1, 0. And if you have the print line after, you're gonna get 0, 1, 2, 3, 4, 5. So I'll trace it, trace through it here. So here we go, we call it with 5. 5 is greater than 0, so countdown 4 is called, and nothing is printed. It doesn't get to the print line yet because it's busy calling the recursive part. Countdown 4 is called, 4 is greater than 0, so it calls 3, nothing gets printed. 3 calls 2, 2 calls 1, 1 calls 0, still nothing. Finally, when you call countdown 0, 0 is not greater than 0, so it doesn't do the recursion. So then it comes down and prints a 0. And then it goes ahead and prints, it goes backwards, kind of, yeah, it's like it spools it up and spools it out, but kind of in the opposite order. It's trippy. It makes, so somebody says, why does it make it go backwards? It's because it's saving all these results on what they call in programming on a stack. And then, so it just keeps putting these things on there. And then once the recursion is over, it's going to have, all it's got left is all these print calls, but it's doing them in the order they were last on, first off. It's like it doesn't go back to where it started. It just kind of unwinds this stack of things that it did. Imagine if you put a bunch of papers on top of each other, made a stack of paper, then the easiest way to get the paper off there is to take them off from the top. And you're just kind of undoing the order. It's a little bit crazy. I'm not going to deny that. And on that term, it's a good idea to trace these things on paper rather than to try to imagine them all in your head. But typically, though, in terms of the forward versus backward thing, the key is if the print call is before or after the recursive call. If the print call is before the recursive call, it tends to kind of go in a forward motion, right? It's printing on the way, like before each recursion call, it prints something. That's sort of logical and forward. And if the print call is after the recursion call, you're going to have it be backwards. And it's not all about printing, but that's, and again, there's no single rule. You can't just say Mr. Hayes said, if it's a print and it's after, it's always going to be backwards. I can't. This is this is dark magic, you know. Not evil. We haven't gone over to the dark side, but it's not always super intuitive. Okay, so that's it for our notes. I'm going to stop that recording.